Good morning, everyone. We have another class today, and our invited speaker is Professor and Dr. TercioAmbrizzi. Professor Tercio, please, can you introduce yourself for the for the audience, and you can start.
Okay, thank you very much, Professor Michele. It's really a pleasure to be here and with all of you. I am a full professor at the Institute of Energy Environment nowadays. I used to be at the Institute of Astronomy, Geophysics, and Atmospheric Science, but then now I just moved this institute, mostly because I'm just creating a new center at the University of São Paulo, which is the Center for Resilience on Climate Crisis and Streams. And hopefully soon you'll be hearing more about this center. So I've been working with climate change and climate variability and climate dynamics for many years. I did my PhD at the Reading University in England. And since then, I'm at the University of São Paulo most of my life, actually. That's it.
You can share your screen with us.
I will.
And go ahead. Yeah.
Let me see how I do it. Aqui. Ok, janela, acho que vou fazer tela cheia, porque aí eu consigo botar em full screen.
Yes, we can see your screen.
Okay.
Yeah, and the presentation also.
Is it full?
Yes.
Good. Yeah. Laser pointer.
Yeah, perfect.
Okay, can I start?
Yes, you can start.
Okay, thank you, Michele, and good morning, everyone, or good afternoon, or good night, depending on which part of the world you are at this moment, or in the future, because this class is being recorded. Well, today I'm just, as the title is saying, that I'll just go through some reflections about the Southern Hemisphere general circulation, talking about some impacts and patterns on large to regional scales, and my focus will be on South America. But I'm also starting to show some teleconnections all over the world. Okay, and just starting. Well, the Southern Hemisphere atmospheric circulation is really fantastic. You have many systems acting. My focus will be, of course, on teleconnection patterns, and then I can talk a little bit about the ENSO, El Niño Southern Oscillation, Madden Julian Oscillation, and some others, which is quite interesting. But also we have the cyclones and anticyclones in our hemisphere, that they are very important and have some impacts on the South America. We have atmospheric blocking, cold surge, and many others. So what I'm going to do is just show some examples based on papers published all over along the years. And if you are watching that, you know that your paper is quite important, and I didn't mention. Don't be angry. I mean, it's really just giving you a flavor. Yeah, at the end of my talk, I will give you a hint how you can really get more insight over all the systems I'm going to talk about. Well, just starting to give you an overview of the Southern Hemisphere general circulation. This is a very nice picture. I apologize that is in Portuguese. Actually, this picture was in English, but then I translated the Portuguese for my class here at the university. But I didn't find the English version, so I put that. But if you are a little bit familiar with the circulation and the southern hemisphere winds and others, this is not going to be so difficult. Here we have the Walker circulation here in the equatorial region. It is clear also the three very strong convective regions, one linked to the West Pacific, linked to this sea surface temperature there, which is very warm, and we also have the rainforests over the African region, and the most famous, actually, the Amazon rainforest here in the southern hemisphere. And as you can see, you have a strong convection, then the wind, the vertical wind goes up, and then goes down here in the East Pacific, and also here in the West Indian Ocean. And since the air is going up, it's also coming towards the poles. But then you have, since our planet is turning, has some movement, then you generate these cells. The Hadley cells, the most famous, because you have the warm air going up and then coming to the south and coming down here, more or less at the mid-latitudes. We also have this Ferrel cell that is a thermal movement cell. That the air comes here from the equators. It's warm than the air here near the pole, and then they get together. And since the warm air is less dense, that goes up, and then you have this new cell. Because of the conservation of the angular momentum, when the air is coming towards to the south, you generate a jet, a very strong jet here at the mid-latitudes. So this is an overview how the circulation, how is the circulation here in the southern hemisphere. And I'm not going to talk about, of course, the ocean circulation. Around the Antarctica, we do have currents, very strong, very important. But in this talk, I'm not going to talk about the ocean, just the atmosphere. And there are many systems that can impact the South American climates, and then also they are related to the teleconnections. The most known is the El Nino, and El Nino is a warming SST here in the central towards the east, near the west coast of South America. Nowadays, we know that the El Nino can have some different features. For instance, the Modoc El Nino is when the SST is more stronger near the Central Pacific, and there is also a mixed El Nino that is more weak, but it also can impact South America in some ways. We have the Pacific Decadal Oscillation, also linked to the SST and the variability of SST. I'm going to talk about the relationship between this PDO, for instance, and the El Nino. Now, we have the Atlantic Meridional Oscillation, which really relates to the variability of the SST in the North Atlantic. We have the Tropical Atlantic Dipole, which is quite important because it's going to have an impact on this intertropical conversion zone, and the position of the tropical conversion zone is quite important for South America, particularly in the north and northeast of part of Brazil, where the rain season depends on the position of this ITCZ. We also have an extratropical Atlantic dipole here, and the position, the sign of this dipole can influence the precipitation here in Brazil in a very strong way. And we also here in the southern hemisphere, we have the southern annular modes. So that it has a variability between high and low pressure over the Antarctica and the mid-latitudes, and depending on the sign of the southern annular modes, you can have an impact on the cold fronts that propagate here in this South America. And then one of the most famous is the Madden-Julian oscillation. Was published first by Madden-Julian in a paper in 1972 that shows, based on the observational data in some stations along of the equator, that there is some variability, and this variability has a timing of between 30 and 50, 60 days. So some people call it an interseasonal oscillation, but because they were the first one to really show that there is this variability in the equatorial region, usually call them Madden-Julian oscillation. But see, this Madden-Julian oscillations is a convection that can walk around the equatorial region, and as it is moving, it can influence the precipitation in that region. I'm going to talk about a little bit more about that later on. And the Indian Ocean dipole. We also have in the Indian Ocean, we have a dipole. This can change the sign. It's quite important for the variability of the precipitation in Australia, in Africa. But also, I'm going to show you that this dipole can influence the climates, temperature, eventually precipitation in the South America. So this is a very nice example of teleconnection patterns linking Indian Ocean to South American climates. Well, this is from a paper led by Michel Reboit and co-authors. Very nice indeed, and see if you want to know a little bit more about these systems in particular and how they can influence South America, please go to the paper. So this is just again an overview of the atmospheric systems that act over South America. When we look at the lower troposphere, in South America, we do have the South Atlantic Convergence Zone, which is quite important. It's a convective band of clouds coming from the Amazon region towards the southeast part of South America. We have also mesoscale convective systems acting in many regions in South America, particularly in the Amazon region, even here over north Argentina and other regions. Cold fronts goes and pass by to the east side of the South America. We have the South Atlantic anticyclone, very strong high pressure here. Also, you have the South Pacific anticyclone. They also can influence the precipitation here around the Chile basically. And we have the trade winds. The trade winds bring humidity from the ocean, which together with the evapotranspiration of the Amazon forest, we do provide a lot of humidity, and this humidity is carried on by the low-level jets towards the southeast part of South America and also towards Brazil. It's quite important to generate precipitation over there. At the upper troposphere, it's interesting because in this region here in the Bolivia, we have the humidity during the summer. We have it's quite warm. Then we generate a convection there, and then what we call the Bolivian high here. And this Bolivian high generates a circulation that creates northeast vorticity, and the variability of this vorticity can impact the precipitation northeast of Brazil. But also, South America have two jets passing by. One is the subtropical jet, and the other is polar jet, or subpolar jet. They are very important, as I'm going to just talk about the waveguides. They can really bring systems through these jets and then influence the climate in these regions here, particularly in the southern part of Brazil. Well, let's talk a little bit about really teleconnection patterns. And let's go to the basic. So the word teleconnection means connection at a distance. This does the teleconnection analysis includes a global vision of the atmospheric circulation in which local forces or instabilities acts to influence remote regions in the atmosphere. It also can be used to study large-scale fluctuations in low-frequency bands of the atmosphere. So teleconnection studies are a good example of the relation between observation, theory, and models. I'm going to show you that just in a moment. But for curiosity, this is a kind of diagram that Rosby was working in December 25th, 1949. You see, a good researcher can work even during the Christmas time. And this is interesting because what Rosby was doing was to calculate the propagation of the planetary waves and its phase velocity and its group velocity. And later on, in the 60s, the planetary waves start to be called Rossby waves in a way that's to consider who really did the first calculation of that. Well, having said that, I'm not going to call planetary waves, I'm going to call Rossby waves all the time. We can understand how does it work, this propagation, in a qualitative way. For instance, if you consider the absolute vorticity, which is the relative vorticity plus the Coriolis parameter, assuming a conservation of the absolute vorticity, you can get, for instance, this variability here based on the variability of the Coriolis parameter with latitude. So if you do a perturbation of in one point of the circulation, this perturbation will generate a circulation that's going to bring high vorticity from the northern part to the south and low vorticity to the south. And this generates what anticyclone circulation, which is basically a low vorticity, positive vorticity, and then this vorticity is going to be propagated to the west, is that. So induced field of meridional velocity due to disturbance of the field vorticity. So the vorticity is going to induce meridional velocity, and then you're going to have a propagation to the west. And but if you look at the basic theory, and this was done by some of papers from Rosby in 1939 and 1945, we can use a barometric vorticity equation. I know if you are not familiar with this equation, that's okay, don't worry. It's just to give you a flavor that there is a theory behind all these ideas of wave propagation in the atmosphere. So we can use, suppose a basic state, climatological U and a disturbance, and then we use also a string function to apply for the barometric equation. And then to solve this equation here, we use a wave solution. And when you do that, you can find the dispersion relation equation and the phase velocity, which is the dispersion relation divided by the wave number. So the phase velocity of the Rossby waves, as you can see, depends on the beta, which is the variability of the Coriolis parameter in the latitudes, and the wave numbers. And as you can see here, there is a negative sign. And the negative sign indicates that the propagation, the phase propagation of these waves is to the west. But then, if you divide this, the relation dispersion by the wave number, then you can get the group velocity, which is the representation of the propagation of the energy of these waves. And it's interesting that the group velocity is positive, so the energy propagates towards east. It also depends on the wave number and the beta. This indicates that these waves are dispersive waves. It means that they cannot preserve its form as it propagates. But if we consider that the phase velocity is zero, it doesn't change, we can get the stationary wave number, which depends on the beta and the U bar, the zonal mean climatology. And if you play a little bit with these equations, you can get to the equation of the waves of curvature of the wave trajectory. And this R depends on the wave number, but also the variability of the wave number in latitude. This is quite interesting. This was done by Hoskins and Ambrizzi in 1993. What they did was to show that depending on the basic state, the atmosphere, the circulation of the atmosphere, the waves can have different behaviors. And the most interesting one is this one here. If you have a region, or if you have a maximum Ks flanked by minimum one, this region here can become a waveguide. So if you know that there is a waveguide in some regions in the atmosphere, you know that if the energy is a wave gets there, it's going to be moved in these waveguides to the other region. So this is a very good idea to calculate or to forecast the weather if you know that there is a waveguide in some regions. Well, this is the theory. In terms of observation, perhaps the most important paper in terms of teleconnection patterns was given by Wallace and Gessler, 1981. What they did was just consider the northern hemisphere winter, 1 month, January, and they did what they call the correlation point. Ou seja, they correlate this point with all the other points, then they move to another one, all the other points, and then they create a teleconnective map showing that which region is connected to the other. And one of the most famous one is the Pacific North American pattern. It means that if you perturb the atmosphere in this region here, you get this, you're going to impact, for instance, the south of North America. So you have, for instance, positive, negative, positive, and negative here. So depending on the force in here, you can actually affect the weather and the climate here in the south part of North America. And they also found the West Pacific pattern, the East Atlantic pattern, in the European pattern. That depending on the wave where it's generated, it can affect the European region. So this was a very important paper showing that in the atmosphere there are regions that they are related to each other, just like the definition of teleconnection. And another paper that was published in the same year was by Hoskins and Caroli, David Caroli. This is part of the David PhD thesis he did with Brian Hoskins at Reading University as well. And what he did was to use a baroclinic model. So it's a model, is dry one. There is no convection in this model. It's just a dynamic model. So you put a force in there, a thermal forcing, and it can generate waves that's going to propagate to other regions depending on the basic state. And what they did was exactly that. Putting a force over here, they can see the waves propagating to another region here. And then they calculate what they call the ray tracing. Depending on the wave number, you can see how the waves are going to propagate. Large wave numbers, usually the waves propagate towards the equator. It cannot propagate further north. And the small wave numbers, it means large wavelength, they can propagate more to the north. So this is a figure of that. And of course, this propagation depends quite a lot of the basic states. So where the this forcing is going to be put in the atmosphere. Well, if you have beta, if you have u, if you this the square root of these two gives me the ks, the stationary wave number, and then you can see stationary wave patterns in the atmosphere. This is for December, January, February, June, July, August. It's interesting because, for instance, for December, January, February, which is summer in the southern hemisphere, winter in the northern hemisphere. As you can see here, is a region where the Ks is bigger, around 8, 9, flanked by regions where the Ks is smaller, 3, around 3. So this is a really serious candidate to become a waveguide in the atmosphere. And since there is this lag here, this space here where there is also the possibility of propagation interhemispheric in this region here during the Austral summer. And for the Austral winter, it's interesting that we can see there are two waveguides, one linked to the subtropical jet, and the other one linked to the subpolar jet. And both can interact and even affect the weather and climate in the South America. So when you have this picture of the wave pattern, the stationary wave patterns, you can have an idea how the waves are going to behave in this kind of states. And what Su and Lee have done in 1991 was to do the same calculation as Wallace and Gustafson have done 10 years afterwards. And so here they calculate also the lag relation to see how the waves move in the atmosphere. And they did that using observational data for the whole globe. And this was the pattern they found. They also found the PNA pattern, the European pattern, but they found other patterns as well. And for the June, July, August, Ambrizzi and co-authors have done the same kind of analysis and also could find different patterns during the Austral winter. And this is some barotropic model. A barotropic model is based on the barotropic-Bautista equation. But you simulate using just one level. And when you do that with the models, as you can see, the patterns that the model reproduce is quite similar to the observational one. And that's why I was telling you that teleconnections gives you a good interaction between observation, the theory, the wave theory we just saw, and also the modeling. They come together quite nicely. Now, more recently, for instance, Lee have calculated also the interactions of teleconnection patterns between Pacific and Indian Ocean, Pacific towards the Indian Ocean, and how this can impact the Australia. In fact, they were looking at how the South America could impact Australia through teleconnection patterns. So they calculate the precipitation, the temperature, even the wave activity flux, showing that a forcing on this region here can generate a wave that can get here to Australia, eventually also impacting the south of Africa. And this just show the Rossby wave number, the Ks here, how that's showing that there's really exists a waveguide here. That's why you can get here to Australia. But a direct link between South America and Africa, particularly South Africa, was done by Green and Reason in 2015. And what they did was showing that the precipitation here in the Northeast Brazil, for instance, has a very strong link with the South Africa precipitation here. And so they just show the OLR for the summer, in this case here, and also 5 days before the maximum here. And what they show that's really the precipitation here, there is a link with the precipitation in South Africa. And then they calculate the string function. And it is clear that we have this propagation here from the northeast part of Brazil towards South Africa. Then there is this relationship. Here is just the same, but using green functions to reproduce that. For the winter, again, what they show that the precipitation here in the southeast part of Brazil has some relation to the precipitation of South Africa. Here again, 5 days before, lots strong OLR, negative OLR here, meaning strong precipitation, and some precipitation over here, and then 5 days afterwards, you see a strong precipitation over here. Again, you can see through the string function analysis this teleconnection between the South Africa. That's just an example. That's one region. If you have one region with strong convection, it can affect another region, particularly here, one continent can affect another continent. So, but it's not only that. We know that the tropical, the equator has a very strong convection, and this convection can generate waves, particularly Ross waves, that can propagate towards north, south, and north. So, and one very good example of this kind of forcing is indeed the Madden-Julian oscillation. Madden-Julian oscillation is a convection propagating along of the equator, given turning around the globe in around 40 to 50 days, actually. This one starts, let's start here, starts in 1st of January 2004. And as you can see, there is a propagation here, strong OLR negative, and as it's going to propagate, it's going to affect the precipitation, particularly in the north part of Brazil. But it's not only that. As the propagation moves along the equator, it's actually generates a wave, Ross waves, disturbs the basic state over here, and then, as you can see, generate waves, and these waves is going to get also in the South America. One very nice work, this is part of the PhD thesis of Simone Ferraz. What she did was to use filters, but also calculate the ray tracing, forcing over here, how the waves behaviors. So she depend on the different frequencies. What she did would show that you do have forcing over here, the waves propagate towards the South America and influence the southeast part of Brazil, where we have the South Atlantic convergence zone during the summer. When you do that, it's quite clear that this waves propagates is going to affect here the precipitation in southeast part of Brazil. So there is a very nice relationship, tropical, extratropical impacts in this case here. And more clearly, this is a work done by Everaldo Souza that shows 30 days before the convection arrives in South America, you can see there is any sign of precipitation anomaly. 25 days negative, 20 days very strong negative precipitation. So depending on the position of the convection, I can influence negatively the precipitation here in the northeast part of Brazil. As the waves progress, minus 15 days, minus 10, you see that almost there is no negative anomaly, and minus 5 and 0, when the convection is over there, then you can get the maximum precipitation, and as wave is passing by, going towards Africa, again, the precipitation is diminishing and until disappears 45 days afterwards. So this is a very nice example how the Madden-Julian, or the Julian wave can influence the precipitation in South America, particularly northeast of Brazil. Another important forcing in the southern hemisphere is the Hadley circulation. And this was work done by Ana Carolina Freitas. What she did was to analyze the Austral winter Hadley circulation and how the Hadley circulation impacts the stationary Ross waves propagation. So the question is how the change in the intensity of the Hadley circulation impacts the stationary Ross waves energy propagation in the southern hemisphere extratropics. So she used observational data. With the observational data, she calculates composites of 6 strong and 8 weak Hadley circulation case based on the Hadley circulation intensity index, which is the difference between the positive and negative peaks of the zonal wind velocity potential at 200 hectopascal level. So Ross wave source and mid-latitude circulation response at the upper level associated with tropical variability also was considered. So if I get first the strong Hadley circulation case, this is the anomaly divergency with the divergence wind vectors at 200 hectopascal. As you can see here at the equatorial region, you have a very strong divergency, and at the mid-latitudes, we have what? A strong convergence. And there you can have, this is Ross wave source regions where you have the generation of waves, and this can generate this wave number 4 wave here, coming from the Indian Ocean towards Atlantic, passing by South America. So this is for the strong Hadley circulation case. For the weak case, as you can see, the most of the convergence actually is in the northern hemisphere. We still have some convergence here in the southern hemisphere, and the wave number here is 3, so it's smaller than the previous one. It means large wavelength, actually. But in this case here, look at the waves passing through the South America. Before, it passed more aside of the South America, but with the weak case path through the South America. And when we analyze, for instance, the impact of the air temperature, as you can see, for the weak case, we have a very strong positive temperatures here in the middle of the South America, particularly in the south of Brazil, Equator, Peru, most of the Argentina and Chile. And then the part north of South America, we have negative case. For the strong case, we have almost an inverted signal. We have negative temperatures here, almost in the same region, and positive ones in the northeast of Brazil. So yes, depending on the intensity of the Hadley circulation, you can generate wave patterns that can influence the weather and climate in other regions, in this one, particularly in South America. But then what we did, what Ana Freitas did, was really to analyze the regional Hadley circulation and how it can impact the South America. So the idea was to examine the impact of change in intensity and poleward edge of the regional Hadley circulation of South America on the patterns of wind, geopotential height, precipitation, temperature. We also, in this article, did some regional modeling, but most of that observational data analysis. And the period was 1996 to 2011, when we found significant trends of expansion of the straightening of the regional Hadley cell over South America. And then we did composite of straightening and expansion cases, and also some numerical modeling. But first, when you look at the trends of the Hadley circulation straightening, the expansion, actually, we have a feeling that, wow, there is a negative trend. But we have to think that, in fact, the sign here in the southern hemisphere is negative. So what we are seeing here actually is a positive tendency for increasing the strength of the hydrogen circulation, and also a positive trend of the expansion of the hydrogen circulation. In fact, I'm not going to show here or discuss climate change, but some recent work have shown that what's happening with our planet more warm is that the tropical bed is expanding, and then the hydrogen circulation is also responds to that. In this case here, we did some SST anomaly analysis for the strong case and for the ones with poleward expansion. And what you can see that indeed the Atlantic have a very strong positive SST for the expansion, not necessarily, but still positive SST. So of course there is a relationship between variability of the SST in the equator, around of the equator, and the circulation. And when we look at the strong ascent branch for the straightening, we can see here between equator and 5 north a very strong ascending motion, and a very strong expansion as well in this region here. So it's really very nicely correlated. And we did also some analysis for the temperature, also precipitation. And you can see that when the strength, with the strength of the hydrogen circulation, you increase the negative precipitation in this region here, in the southeast part of South America, particularly south of Brazil. And for the expansion, we just increase, it's very similar to the straightening, but you have a more strong area that's with negative precipitation. Another interesting work done using this idea of teleconnections and the propagation and waveguides was done by Gabriela Miller, her PhD thesis. What Gabriela had is sometimes during the winter there was generalized frost here in the central part of Argentina. It's quite important for agriculture, for instance. And she wants to know why there are winters that you have generalized frost, and there are some other winters that you don't have. So what she did was actually to calculate the meridional wind 3 days before the generalized frost until the day that you have the maximum frost over there. And as you can see here, 3 days before, there is a clear Rossby waves propagation towards South America, and also there is some hints that there is in here suggesting that the propagation is along of the subtropical waveguides linked to the subtropical jet, and some energy also propagating the subtropical polar waveguides. So -2 days, -1 day, and for the day 0, what's happening is this wave here in the subpolar subtropical jet and the one propagating the subpolar waveguide get together and creates a very positive and strong meridional wind that brings polar air towards the middle of the Argentina, and then we have a generalized frost. And what she did also, she used that same baroclinic model that Hoskins Caroni had used many years ago to put forcing here at the entrance of the subtropical waveguide and the entrance of the subpolar waveguide, and simulated that, and indeed the model could reproduce the same kind of pattern that generates that generalized frost. Still very interesting indeed. And this is just a representation what the model was giving together with what we were seeing in the observational data. So a schematic, a conceptual model that's why there is this generalized force over here in the North Argentina. Another very interesting example occurs in 2013, 2014, the summer of this period. This red line here represents the water reservoir in the São Paulo city, metropolitan São Paulo city. And this reservoir provides water for more than 9 million people in the city. And as you can see here, the reservoir is almost full in 2010. So it starts to decrease. It got to almost zero in 2014. This is the precipitation. There is no precipitation in 2014. And then we had water crisis in the city, and so on. But the question here is, why didn't rain? What's happening over there? So this is the precipitation anomaly. This is the geopotential height, which shows an indication that there is a wave coming here from the Pacific. And this is the stationary wave number and the ray tracing, showing that the forcing in this region here generate a wave pattern that gets here to the southeast of Brazil. In a conceptual model, what's happening that we saw there was a strong convection here, which is affecting, perturbing the atmosphere over the, more or less, the central part of the Pacific. And this generates a wave that was almost stationary, that creates here a kind of high pressure blocking. With this high pressure blocking here, was not allowing the cold fronts going towards north. They were just coming towards the South Atlantic, and also the humidity from the Amazon region was not allowing to come towards the southeast. It was just coming to the south, and then we didn't have any South Atlantic conversion zone during this period. The South Atlantic conversion zone during the summer in the South America, and particularly in Brazil, they are quite important because they are a very strong cloud band that generates a lot of precipitation. And around 60 or 70% of the water reservoirs in southeast of Brazil depends on the precipitation during the summer because of the South Atlantic conversion zone. So if you don't have that, it doesn't rain, so you do not have water in the reservoir. So this is quite clear how we explain why it didn't rain, and that this was related to some disturbance in the Pacific region that was affecting here South America. But of course, the teleconnection pattern most famous is the El Niño. That's an oscillation, El Niño and La Niña. And here is the representation of the circulation. The blue arrows and red arrows represent the normal circulation here in this region of the equator, and here over the South America. And the black arrow, it just represents the modification of this circulation when we have a strong SST positive anomaly in this region here, from the central to the east part of the Pacific. Here is more clear during a normal period, and here when we have a convection there. So as you can see, there is a complete modification of the circulation when we have an El Niño acting over there. And what's happened, there is an impact generating more precipitation in the south part of Brazil, for instance, in the north and northeast part of Brazil, less precipitation. This is for December, January, February, and also for March, April, May, when it gets more stronger. The precipitation in the south and less precipitation in the northeast part of Brazil. This is the representation of the SST in this region. So when you look at the circulation, what's happening that with the strong forcing over here, generates a stationary wave that gets over here and favors the precipitation in the south of Brazil. On the same time, here, if you look at the vertical velocity, here we get a strong descending branch of this ascending branch over here, and therefore impacting the formation of clouds and precipitation in the northeast part of Brazil. And in another way, we have ascending branch over here, and then precipitation in this region here. Here, for instance, is the omega. Omega represents the vertical velocity, and divergence of Q is another way to represent convergence and divergence in the vertical. And when you have El Niño, what we do have is you modify the position of the zonal winds. And as you can see here, in a composite of El Niño, the black arrow, the black line here is the climatology. The dash one here is the El Niño. As you can see, during the El Niño, the zonal wind is stronger. It can be also more to the south compared to the climatology. For the March, April, May, this is happened as well, particularly here for the more south jet stream. And then this is a work by Caio Coelho and co-authors. What they did, they tried to get to answer this following question: which position of the maximum SST in the Pacific affect more the precipitation in South America? And this region here, F and G, when you calculate the correlation between precipitation and SST, shows that when the forcing is in this region here, we have less precipitation, we have a negative correlation with precipitation in the northeast part of Brazil, and a positive one in the south of Brazil. This was confirmed by another statistical analysis, single value decomposition, also showing the same kind of patterns. Of course, this also have some patterns related to the precipitation in the Peru and Chile as well. But particularly in Brazil, this is quite interesting point. So, but one thing I always say is that not every El Niño has its own fingerprint. One El Niño is always different from another one. And to see that, Ambrizzi and Souza had calculated a seasonal standardized index for the Austral summer and autumn, and calculates the precipitation in some key regions of South America. In this region here, 1, 2, 3, 4, 5, and 6. So when you do that, and they get this, they got their news from December, January, February 1967-68 up to El Niño 97-98. And this first figure here shows the first red, the first circle, the blue one, means SSTs in Niño 1, 2, the red is SST in Niño 3, Niño 3 plus 4, Niño 4. This is some regions along of the equator where you can calculate the variability of the SST in that region. And as you can see here, for Niños, what we expect positive anomalies of SSTs in December, January, February, March, April, May, is you can see here in this El Niño, this happens quite nicely. But if you go for the El Niño of 63-64, you see that it started with positive El Niño SSTs in December, January, February, and then got to negative values in March, April, May. And some of the other El Niños, actually, this has happened quite a lot. So some of them, positive one, H2, H3, for a very strong El Niño, and then 97, 98, the strongest in the last century. And then for each one of that region, for East Amazonia and Northeast Brazil, usually, and we saw that, we have negative precipitation during Niños. As you can see, here is the same thing, but we have a line here with zero precipitation. Above, we have positive precipitation, below negative, and the first circle it means December, January, February, the second one, March, April, May. As you can see, indeed, for some El Niños, the precipitation is negative, but there are El Niños that the precipitation is positive. That's for the Eastern Amazon, Northeast Brazil, and South America, where the precipitation should be positive. We can see that there are El Niños that they are negative. So there is a large inter-El Niño variability, and we must be careful when you consider one region and you say, oh, when we have El Niño, it's not going to rain over here. Not necessarily. It's going to depend of the El Niño itself. And what changes from El Niño to another? When you get a composite of El Niños, this is the profile of the SSTs you can find. But when you get specific El Niños, for instance, El Niño 82, 83, which was very strong, you see that the maximum intensity occurred around 130 west. But when you go to El Niño 97, 98, which was the strongest in the last century, the maximum actually is around 100 west. And the distribution is quite different. As you can see here, for El Niño 86, 87, it's around 160, and for 91, 92, around 150. So they have the forcing is in different position. If the forcing is different position, you're going to affect the atmosphere in a different way. And if you affect the atmosphere in a different way, we can have different impacts on the zonal wind, for instance. Look at this, it's quite interesting. For the El Niño 97, 98, you see the zonal wind is quite strong, but it's almost in the same region as the climatological one, in terms of the position. But the El Niño 82, 83 is more to the north, compared to the climatology. So what we expect with that, different impacts for 82, 83. The forcing is over here, and the waves propagate towards South America and gets into the South America, and then they are going to forcing the precipitation in a different way there. In 97, 98, you see that the force is quite strong, but the waves propagate more to the east of South America than through the South America itself. So the impact was really different from this El Niño to this one here. In fact, the south of Brazil suffered much more in terms of floods during the El Niño 82, 83 than the 97, 98, which was the strongest one. And then we can, this is a work by Maganha and Ambrizzi. They use the same barotectonic model to forcing in the same position the atmosphere, the basic state for the Niños, and see that yes, it is possible to simulate this kind of propagation, indicating that the position and intensity of the SST in the Pacific during different Niños can influence the climate and the circulation in South America in a different way. So, what is the relationship between Niños, low-level jets, Pacific Decadal Oscillation, and Martin Julia? The low-level jets, we know that we have the trade winds here, bring humidity, and then pass through the Amazon forest with the evapotranspiration, get more humidity, gets towards here near the Andes region, Andes mountain, and then comes towards the south. During the El Niño, what you can see is this kind of trajectory of the low-level jet, and then it favors the precipitation here in the south of Brazil. That's we know. When you have a La Niña, you see that the low-level jet is less intense, and the precipitation moves more to the north when we compare to the El Niño one. And then when we compare the interaction between the PDO and El Niño, for positive PDO, we can see a more precipitation here in the southeast part of Brazil, and southeast part of South America, and for the negative PDO and El Niño, less precipitation there here, and also negative anomalies more stronger in the southeast part of Brazil. And this is what's happened when you consider interaction between positive El Niño and PDO in terms of SST. That is much stronger, and then, of course, you are going to get a more stronger signal here in this region, as I showed a little bit earlier. If you calculated the integrated moisture flux, the divergence, again, you can see a strong moisture flux towards this region here, where you do have more precipitation, and for the negative one, the moisture flux goes more to the north and less to this region here, and then we can explain why it rains less there. And then, of course, if you calculate the cyclone density and surface pressure, you can see this is surface pressure, blue one is negative, and this cyclone density positive here. During El Niño and PDO positive, you have more cyclones in this region here, and of course also less, the pressure is smaller over this region here, and that confirms that these two together favors more precipitation there. And for the negative PDO, as you can see, everything is more weak. In particular, the surface pressure is positive here in this region. And what about the Madden-Julian oscillation and the precipitation streams? We have then the interannual variability, El Niño. We have the interseasonal variability, Madden-Julian oscillation. You can have different response. This is some papers that have done some work in this direction. So the idea here, this is was a work done by Shimizu and co-authors, is to analyze the influence of the Madden-Julian on the frequency of occurrence and or intensity of extreme precipitation events of the Amazon during the Enso phase. So we are going to focus on this area here, the Amazon region. As you can see, it's a very warm humidity area. We did a composite considering December through May. And this is how, in this region here, is the distribution of the precipitation, the annual cycle. As you can see, during the summer, you have more precipitation and decrease less precipitation during the winter, the austral winter. So what generates this precipitation? Many things. The South Atlantic convergence zone may be important. The position of the intertropical conversion zone here also is important. You can have the Atlantic SST meridional gradient, as you saw, we saw at the beginning, also may be important in this case. Well, what Shimizu did was to use daily precipitation, so CPC, daily wind, humidity, omega from NCAR and SEP NCAR. We use the Madden-Julian oscillation events based on the Wheeler and Hendon index, and for NOAA we've got the Enso phase, the Oceanic Niño index. So we create composites considering only El Niño without Madden-Julian, only Madden-Julian with all phases of Niños and Niñas, we didn't exclude, and only the combination of Enso and the Madden-Julian. In doing that, what we found that it's a clear tendency along of this period of the data we use of the increase of the dry streams and positive tendency to increase dry streams and a negative tendency to decrease the wet streams in that region. And also, the dry and the wet streams depend on the position. This phase here, more or less, represents the propagation of the convection of the equatorial region during the Madden-Julian phases. And what really they found that when you get interaction between El Nino and Madden-Julian, you really can decrease the vertical motion in this region, then you can affect the precipitation over this region. And finally, can Indian Ocean SST anomalies influence South American rainfall? Yes, the Indian Ocean SST variability, particularly the Indian Ocean dipole, can be quite important and influence the climate over South America. And this was done by Sage and co-authors, 2005, showing that depending on the sign of the Indian Ocean dipole, you can have an impact on precipitation over there, in temperature. But it was in the study by Tascheto and Ambrizzi that they show that there is really, when we have a warm basin, uniform basin-wide warming here in the Indian Ocean, that can generate a wave pattern that gets to South America and then influence the precipitation over there. Before this work, all the other works was more focusing on the variability of the Indian Ocean dipole, or even the wide warming basin was more the impact, particularly in the south of Asia or even in Australia. It was worked by Tascheto that really show this influencing how Indian Ocean can influence the climate here in South America. And I told you about cyclones, and there is a relationship between teleconnection and trends of that. One of these work shows, for instance, the cyclones nowadays. If you calculate the number of cyclones in the southern hemisphere, they are not changing too much. But if you just calculate the most strong cyclones, then you can find a very nice positive tendency on that, particularly during the summer and autumn and some periods, and a little bit tendency for winter and spring. And this work actually was a extension of their previous work done by Pesa and Ambrizzi many years ago. But also, here is quite interesting, when you do a partial correlation between cyclones density and ENSO, and remove the southern alarm modes and the Indian Ocean dipole, you can see that there is a tendency to increase cyclones here in the southeast part of the Pacific. When you calculate the cyclones density, the cyclones density with the sun, removing ENSO and the dipole effects, as you can see, there is a positive cyclones tendency here near the coast of South America, which is quite important and interesting because it can directly influence the precipitation over there. And then you do a cyclones density correlate with the Indian Ocean dipole, removing ENSO and sun, again, close to the east-west of South America, we have a positive tendency over there. This was a work done by Michel Reboit and co-authors, 2015. So it is clear that there is this relationship. What's happening in one region can affect cyclones in another one in such a way that this can be quite important in terms of impacts and the streams of climate over South America and other regions, of course. Well, I just briefly mentioned a few atmospheric systems that can influence the South American continent and the atmospheric circulation in the Austral hemisphere. Of course, these systems also can impact other continents in the Southern Hemisphere, Africa, Australia, and even Antarctica, and I didn't touch that. However, if you want to have a complete review of these systems and others, don't worry. I have the answer for you. In fact, hopefully, by the end of this year, the book Meteorology and Climate of the Southern Hemisphere will be published by the Cambridge Academic Press. This book provides a comprehensive review of advancements in the climate and weather knowledge. It presents an extensive literature review highlighting both high-impact papers and fundamental studies. The book brings together an excellent team of scientists who are experts in the Southern Hemisphere weather and climate, with many contributors based on leading universities and institutions in the region. This book was edited by Andrea Taschetto, Tando Nadarana, and TercioAmbrizzi. You are seeing in the first glance on the cover of the book, and the book has 13 chapters, each chapters showing the general circulation in the Southern Hemisphere in different aspects. It has circulation around the Antarctica, in all the continents, the mid-latitudes, the tropical ones. It discusses not only the climate variability, but also the climate variability. It's changed because of the global warming. So I'm sure that you can find most of what I just show you here briefly in details, using the state of the art of the science for that. So having that, thank you very much for your attention and the opportunity. If you have any questions, I'm glad to answer them. Thank you.
Thank you, Professor Tercio. I will stop the recording now, and we can move to the questions, okay? Camila, just a second, I need to stop the recording, okay?
Okay.